Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. So, in this lecture, we are going to discuss micro program example. So, in the previous sessions, we have discussed about the control memory and how to implement the control units. So, already we have discussed about the control memory. Okay. So if you consider any basic computer, mainly it has three functional parts that are CPU, central processing unit, memory, input and output devices. So if you consider a CPU, again it has three important parts. So that are ALU, arithmetic and logic unit, control unit and registers. So here in the CPU, the control unit it plays a very important role. That is, using this control unit, it can be used to initiate a sequence of micro operations. Okay, so that is the importance of the control unit. So mainly the control unit is used to initiate the a sequence of micro operations, and also it is used to generate timing and control signals. Okay, so uh, once the configuration of the computer and its microprogrammed control unit is established, so already we have seen the control unit. It can implement in two ways. One is a hardware control unit, and second one is a microprogrammed control unit. So hardware control unit means in this the timing and control signals are generated using the hardware components like some logic gates, encoders, decoders, multiplexer, demultiplexer. So these are all the different hardware. So by using this hardware, we are generating the timing and control signals. So that is the hardware control unit. So on the other hand, microprogrammed control unit. So microprogrammed. So the name itself it specifies the meaning microprogrammed. So that means here the timing and control signals are generated by using some micro program. So micro program. So this micro program we are storing in the control memory. Okay, control memory. So what is control memory? The memory which is present in the control unit. So that is called control memory. So in that control memory, we are storing this micro program. Okay. So the micro program. So micro program we are storing in the control memory. So what is micro program? Micro program is a collection of micro instructions. It is a collection of micro instructions. Okay. So every micro instruction it contains one or more micro operations. Okay, so that is a sequence. So how the micro program will generate a micro operation. So that is a relation between the micro program and the micro operations. So once we have okay, so once the configuration of the computer and its microprogrammed control unit is established, then the designer's task is to generate the micro code for the control memory. Okay, so this code is the code generation is called micro programming. So this the generation of this micro code is nothing but it is a micro programming. It is very similar to the programming conventional machine language programming. And for each instruction of the for each instruction of the instruction set of the CPU, we will have a micro program. So in general, the CPU having some processor. So the processor is having some instruction set. Instruction set means a group of instructions. So for every instruction, there is a corresponding micro program. Micro program. Suppose if you have an instruction add. So add is one instruction. So in order to perform the add, so the corresponding micro program or micro routine should be there. Okay, so the corresponding micro program has to be done. Okay, in order to perform the add micro operation, the corresponding micro program has to be run. So that's why this micro program is required. So coming to the computer hardware configuration. So the computer mainly it consists of the two types of units. One is the processor unit and another one is a control unit. So this is the area represented with the dotted line. So this is a control unit, and the remaining is a processor unit. So total it contains two types of units. One is a processor unit and another one is a control unit. So and also this computer hardware configuration, mainly it is having two types of memories. So this is one of the memory, that is a main memory, and it is a control memory. So uh, we have seen two types of memories, main memory and the control memory. So main memory it can be used to store the instructions and the data. So instruction is nothing but machine instructions, and the data we can store in the main memory. And the size of the main memory is the 2 kilobytes. 2 kilobytes. Okay. And the coming to the control memory. So the control memory it is used for storing the micro program. Micro program. Micro program is nothing but a collection of micro instructions. And the size of this control memory is 128 volts. Okay. So coming to the block diagram. Okay. So see here. So this is a main memory. So what is the main memory size? It is a 2 kilobytes. 2 kilobytes means 2048 bytes. 2048. So and the size of memory word is 16 bit. 16 bit. That means in every memory location we can store 16 bits of information. So that is the meaning of this 16. And similarly, looking to the control memory. So control memory is the 128. That means the control memory totally it contains 128 words. That means 128 memory locations. And in each memory location, we can store 20 bits of data. 20 bits. 20 bit in every memory location, we can store 20 bits of data. Okay. And some 4 registers are associated with the processor unit, that are address register, program counter, data register, accumulator. So these are the 4 registers associated with the processor unit. So this is entire this area is the this block is the processor unit, and 2 registers are associated with the control unit. One is the subroutine register and the control address register, CAR. Shortly we can call CAR and SBR. SBR means subroutine register and CAR means control address register. Okay, and see here. So if you look into the data register, so the data register it can receive the input from different registers. So this data register it is receiving the input from the address register and the program counter. So from the address register to the program counter, and from the program counter it will be to the data register through the multiplexer. So already in previous sessions we have seen about the multiplexer and its working. Okay. So in multiplexer, based on the selection lines, any one of the input will be connected to the output. So that is a multiplexer. And also the data register it receives input from the main memory also. And also the data register it receives the input from the accumulator. So from the accumulator, so it is receiving through the multiplexer. So accumulator through from the accumulator it is receiving the data register through the multiplexer. Okay. Okay. So this is about the computer hardware configuration. Okay. So total 4 registers are associated with the processor unit and 2 registers with the control unit. So the 2 registers are SBR, subroutine register, and CAR. And with the processor unit, 4 registers are associated. One is the address register, program counter, data register, and accumulator. So these are the 4 registers associated with the processor unit. Okay. So the control memory and its registers are organized as micro-programmed control units. And the transfer of information among the registers in the processor is done through multiplexer rather than common bus. So here the connections between the registers we can do it using 2 ways. One is using conventional common bus system, and the second one is using the multiplexer. So here we are transferring the data from one register to the another register through the multiplexer. So here we are using 2 types of multiplexer. This is one and this is a 2. So here we are not using any a common bus system. We are not using any common bus system because the common bus system, it requires more number of connecting wires. So that's why we are not using this common bus, and we are using a multiplexer. Okay. And coming to the instruction format. Instruction format. So it consists of 3 fields. So already we have an instruction format. So if you look into the main memory. So what is the main memory size? 2048 into 16. So that means what is the size of the instruction? The size of the instruction is 16. Size of the instruction is 16 bit. Okay. So this 16 bits are dividing into 3 fields. Divided into 3 fields. Okay. So these are the 3 fields. So the first field is a address field. Address field. So this address field is from 0 to 10. 0 to 10. So this is 0 to 10. So that means total 11 bits. Next field is the opcode. Next field is the opcode. So opcode, it specifies the operation to be performed. So for this opcode field, it requires it occupies 4 bits. 4 bits means 11th bit, 12th bit, 13th bit, 14th bit. So total it occupies 4 bits. And next one is 15th bit. So 15th bit is it is I. I means indirect bit. That means whether the instruction is having direct address or indirect address. So that will specify this. So if I is equal to 1, that is a indirect address. So if the instruction is having indirect address, then we need to go to the memory in order to calculate the effective address of the operand. Suppose if I is equal to 0, then we can get the address of the operand directly. So if I is equal to 0, that represents direct addressing. And coming to the opcode. So already we know. So here opcode, in the opcode field 4 bits are there. 11, 12, 13, 14. So total 4 bits are there. So that means using that 4 bits, we can perform 16 operations. 16 operations. So that means 2 power 4. So total 4 bits are there. So 2 power 4, 16. So total 16 operations. 16 operations we can perform. And this address, it represents the address of the operand. Okay, so this is about the instruction format. So the instruction is a command to the processor to perform some specific task. Okay, so the size of the instruction is 16-bit and it is divided into three fields. The first field is a address field, and second field is a opcode field, and the third field is a indirect bit. Okay, so total here we can perform 16 possible memory reference instructions. Suppose if you consider a add instruction, add. So the instruction, it adds the contents of the operand found in effective address to the content of the accumulator. So the branch instruction causes a branch to the effective address if the operand is in AC is negative. Okay. So see here. So already we have seen the instruction format. So this is the instruction format. So it contains three fields: address field, opcode field, and indirect bit. Okay. So based on these four opcode bits, we can totally we can perform 16 micro operations. 16 operations we can perform. Okay, 16 operations we can perform. So out of the 16, for the simplicity, we are specifying only the four operations that are add, branch, store, exchange. So first one is a add. So for the add, the opcode is a 0000. So that is a opcode. So that means the bits are 11, 12, 13, 14. So the 4 bits are there. That means 2 power 4, 16 combinations. So that are the starting sequence is all zeros. Next 0001, 0010, 0011, 0100 up to the last call sequence is all ones. So when all the bits are zeros, it performs one operation. In the next sequence 0001, it performs another operation, that is a branch. Next, in the next sequence, it performs store. Next, in the next sequence, it performs exchange. So like that, it performs total 16 operations. Okay. So here the opcode field is all zeros. So what is the operation performing here? Here, this add instruction, it performs addition. It performs addition. So M of EA, EA means effective address. Okay. So in order to perform the addition operation, we require two operands. That means two values we require. One value is stored in the accumulator, and another value is stored in the memory. Okay. So we need to calculate the effective address. So that's why M of EA, this add instruction, it performs addition with the operand which is stored in the effective address with the accumulator. After performing addition, again the result will be stored in the accumulator itself. So result automatically it will be stored in the accumulator itself. That is a add. Next, branch. Branch instruction. Branching means transferring the program control from one memory location to the new memory location. Okay, so that is called branching. So when the branching will takes place if AC less than 0, if the accumulator content is having less than 0, that means if the accumulator is having a negative value, then the branching will be takes place. So EA arrow PC. Suppose if the program control wants to shift to the from one memory location to the another memory location. So suppose, see here, you have a memory. you have a memory, and right now you are in the 4000 location. So if you want to shift transfer from 4000 to the some 4500 location, so that means the program control is transferring from 4000 so this location to the this location. So that's why, so this is a effective address, this is a effective address. So this effective address we have to load into the program counter, we have to load into the program counter in order to branch, in order to take the branching. Because whenever this new address is loaded into the program counter, then the program control will be transferred to that location. Because program counter, that means it stores what it will do. Program counter, it stores the address of the next instruction is to be executed. That is a program counter. So after executing the instruction which is in the 4000 location, next we have to execute the instruction which is at the address 4500. So that's why we have to load that new address, that is nothing but 4500, into the program counter. So that is a branching. And next one, storing. Storing is nothing but loading the data from the register into the memory. Okay. So here, okay, for the store, the opcode is 0010. Next, here the description is, so we have a register accumulator. So in that we have some data. So that data we are going to store in the memory. Okay. So to the memory, to which location we are storing that, to which location we are storing that value, that is specified by the effective address. Okay, so the contents of accumulator we are transferring to the memory whose address is specified in the effective address. So that is a store. And next one is a exchange. Exchange. So for its operation, the opcode is 0011. Okay. So exchange. That means here the contents of registers and memory are gets exchanged. So here, see here. So here we have a effective address. Here the content which is present in the effective address will be transferred to the accumulator, and similarly the data which is present in the accumulator is transferring to the memory whose address is specified by the effective address. Okay, so that means the contents will be exchanged between the accumulator and the memory whose address is specified by the effective address. So these are the four operations out of the 16. So like that, total 16 operations we can perform. And coming to the micro instruction format. Micro instruction format. So the micro instruction format, okay, so see here. So these micro instructions are stored in the control memory, because just before we have seen the computer hardware configuration. So in that we have two types of memories. One is the main memory and another one is a control memory. Okay. So the size of the control memory is 128 words, and each micro instruction size is 20 bit. Each micro instruction size is a 20 bit. Okay, so that means total we have 128 words, nothing but 128 memory locations. 128 memory locations. So starting with 0. Okay, next 1, like that. The last one is a 127, because the starting address it is started with the 0, so that's why the last value is a n minus 1, where n is a 128. 128 minus 1, that is equal to 127. So total it contains 128 memory locations. And in each memory location we can store 8 bits of information. 8 bits. In every memory location we can store 20 bits of information, because here the size of the micro instruction is 20 bit. So like that 10 11. So like that total it contains some 20 bits in every memory location. Okay, so this is a micro instruction. Micro instruction. So that entire the 20 bits we are dividing into different fields. Different fields. So that are F1, F2, F3. So see here the format, micro instruction format 20 bits. So total 20 bits are there. So the first 7 bits that represents the address of the operand. Okay, so the first 7 represents the address, and the next 2 bits represents the branching, and the next 2 bits represents the condition, and next 3 bits represents field 3, next one represents the field 2, and next represents the field 1. So here this is a opcode. It is a micro opcode field. Opcode. So total. So this total 9 bits is it represents the opcode field. So these 9 bits we are dividing into 3 fields, that are F1, F2, F3. Okay, F1, F2, F3. So the size of each field is 3 bits. Next 2 bits is condition. It represents condition. Next 2 bits represents branching. Okay. So F1, F2, F3 are the micro operation fields. CD condition for branching, and BR branch field, and AD address field. So this is a micro instruction format. Okay. So see here. So here every field, every micro operation field is having 3 bits. 3 bits. So with 3 bits it can perform 2 power 3. 2 power 3. So 2 power 3. So 2 power 3 means that is equal to 8. So using this F1 field we can perform 8 micro operations. Similarly, using F2, 8 micro operations we can perform. Using F3, we can perform 8 micro operations. So that means total we can perform 24 micro operations. But in every field, the first micro operation is a NOP. In every field, the first micro operation is a NOP. NOP means no operation. So that means in 3 fields, the first 2 condition is a NOP, first micro operation. So that means 3 NOPs are there. So that means 3 micro operations we are not using. So 24 minus 3, that is equal to 21. And in the F3, the last micro operation is it is unreserved. It is a reserved. Reserved means it can be useful for the future purpose. So that means that the last micro operation in the F3 field also we are not using. So that means 21 minus 1. So that is equal to 20. So that means using this F1, F2 and F3 fields, totally we can perform 20 micro operations. So let's see one by one those micro operations. So this is a F1, first field. Okay. So in the first field, we are having 3 bits. We are having 3 bits. So using that 3 bits, we can represent 2 power 3 operations, 2 power 3 micro operations. So 2 power 3, how much? That is equal to 8. Okay. So what is the first case? 000. It performs NOP. 001, it performs AND operation. What is AND operation? It performs AND operation on the data of accumulator, and it performs the AND operation. It performs the add operation with the contents of accumulator and the data register. Next, clear accumulator. That means we are clearing the accumulator. After clearing, the accumulator content is equal to the 0. Increment accumulator. DR to AC. That means transferring of data from data register to the accumulator. DR to AR. DR to AR. Transferring the data from the data register to the address register. Next, PC to AR. Transferring the data from the program counter to the address register. Last one is a write. Write operation is nothing but transferring the content from the register to the memory. So here, what is the data present in? The data is present in the data register. So from the data register, we are transferring to the memory, whose address is specified in the address register. Okay. So this is about the first field. Similarly, coming to the F2. In F2 field also, we have 3 bits, and totally we can perform 2 power 3, that is equal to 8 micro operations. In that, the first one is a NOP. We are not using the first one. And 001, it performs subtraction. 010, it performs OR operation. 011, it performs AND. 100, it performs a read operation. So read operation means transferring the data from the memory to the register. So this is memory, this is the register. Next, AC to DR, accumulator to data register, increment data register. Next, PC to DR, program counter to data register. So these are all the F1 and F2 fields. So this it performs F1 field, it performs arithmetic operations, and this F2 field it performs logical operations, and the F3 performs shift operations. Okay. So F3 field. F3 also, the first micro operation is NOP. Next, XOR operation. Next, complement, shift left, shift right, increment, program counter, address register to program counter, and when the code is when the micro operation code is equal to all ones, then means that is reserved. That operation is reserved. That means in future, if you want to use it, then we can use it. So that is a reserved. So this is about the F1, F2 and F3 fields. And coming to the condition field. Okay. So the condition field, it includes 2 bits. So 2 bits are used to represent the condition. Okay. So they are encoded to define 4 status bit conditions. As stated in the table, the first condition is always 1 with CD is equal to 0. So total 4 types of conditions are there here. Unconditional branch, indirect address bit, sign bit of AC, 0 value in AC. So first one is a 00. So unconditional branch. Unconditional. The name itself, it specifies the meaning. Unconditional. That means we are not checking any condition. So without checking any condition, then the branching will takes place. So for that, the condition is always is equal to 1. So the condition is always 1, always true. Okay. So it can be the unconditional branch. It is represented with a symbol U, and the condition is 00. So the condition field bits both should be 0 in order to perform the unconditional branch. and next condition is 0 1. If 0 1, it represents that indirect address bit. Indirect. Okay. So that means in order to check this condition, we need to check the 15th bit of the data register. So we have a data register. We have a data register. Data register. So data register size is 16 bit, 0 to 15. So this is a 15th bit. Okay. So suppose if the 15th bit is equal to 1, then the condition is true. That indicates that signifies the indirect address bit. So indirect address means if the 15th bit is equal to 1, then we need to go to the memory in order to calculate the effective address. So that is a indirect address bit. Next one, 10. So 10 is a sign bit of AC. Sign bit of AC. So here, so for this condition, we need to consider a register accumulator. We need to consider a accumulator. Okay. So if the 15th bit of the accumulator is equal to 1, then the condition is true. Okay. 15th bit of the accumulator, if it is equal to 1, then the condition is true. Then the condition is true. So that is represented with S. Okay. And the last condition is a 1 1. So the symbol is AC is equal to 0, and it is represented with a letter Z. And the operation is a 0 value in accumulator. So if the accumulator it holds a value 0, then the condition is true. Then the condition is true. Okay. So if the accumulator value is equal to 0, then the condition is true. It can be represented with a 1 1. So these are the 4 different condition fields. The first one is a unconditional branching. Next one, indirect address bit. Third one is a sign bit of accumulator and 0 value in accumulator. So the conditions are 0 0, 0 1, 1 0, 1 1. Okay. So in the micro instruction, so till now we have seen F1 field, we have seen F2, F3, and we have seen conditional. Next we have a branch field. So branch field. So total here 4 types of branches are there, that are jump, call, return, map. Okay. So first one. So the branch field, in order to the branch field, it is having 2 bits. It is having 2 bits. So 2 bits means 2 power 2, that is equal to 4 cases. 4 cases are there, that are 0 0, 0 1, 1 0, 1 1. Okay. So the first case is 0 0. So when the branch field 2 bits are both are zeros, then it represents jump. It represents a jump. So if the condition is equal to 1, if condition is equal to 1, the address will be loaded into the control address register. Okay. So suppose you can understand with one example. So this is a memory. Okay. So address is some 4000, 4001, here 4750, 4751. Okay. So see here. Okay. So suppose currently if the instruction is executing at a location 4000. So here jump means what is jump? Jump means transferring the program control from one memory location to the new memory location. That is called jump. So if the condition is true, if the condition is equal to 1, so that means before jump instruction, jump 4750. So this is a jump instruction. So before that jump instruction, we have some condition, some jump if carry or jump if below, jump if no carry. So like that, some conditions are there. If the condition is true, then the next instruction will be executed. This next instruction will be executed. So what is next instruction? Jump 4750. So that means if the condition is true, then it will be jump to the address 4750. So that means from this it will be transferring to the 4750 location. So that's why this 4750 address we have to load into the it will be in the address register. It will be loaded into CAR, control address register. Okay. So that is suppose if the condition is not true, what will happen? Instead of going to the 4750, the instruction which is at the next memory location will be executed. So what is the next instruction? What is the next instruction address? That is a 4001. So that is a jump. Next one, call. Next one, call. So this call is used especially for the subroutines. When you have a subroutine. What is subroutine? Subroutine is a function. It is just similar to the C and Java in programming languages. So subroutine is a function. Whenever we call function, then the program control will go to the function definition, and all the statements in that function definition will be gets executed, and after that it will return back to the next instruction of the main program. So that is a call. So see here. So for call, the branch field should be 0, 1. Okay, 0, 1. So suppose you see here, you have a branch. You have a branch. So let us assume this is a 5000. Okay, so this is a subroutine. Okay, this is subroutine. Subroutine address is a 5000, 5001, 5002, 5003. Okay, so let us assume here we have a instruction call 5000. So whenever this call instruction is executed, then the program control will be transferred to the 5000 location. Then the program control will be comes to 5000. So that means here the subroutine is there in 5000 location. Okay, so then the statements in the subroutine will get executed. So in the subroutine, the last instruction. So the last instruction is that is a RET. The last instruction will be RET. Whenever the last instruction RET is gets executed, then the program control will be returned. The program control will be returned back to the next instruction of the main program. So what is the next instruction? Next instruction is at the 4001. Okay, so that is a call, and the next one is a return. So whenever we have called the subroutine, see, if the condition is true, what will happen? It will go to the subroutine. So in order to go to the subroutine address will be given to the control address register. Okay. See, so the address will be loaded into the CAR. So what is the address here? It is a 5000. So this is address. So this address I am loading into control address register, because if that address is loaded into the control address register, then the instruction which is in at that location will be executed. Okay. Next. So CAR plus 1. CAR plus 1. Okay. So CAR plus 1. So next instruction will be loaded. SBR. Because whenever the program control is transferred from whenever the program control is transferred from 400 to the 5000. Okay. So after performing the subroutine, after executing all the statements in the subroutine, it has to return back to the 4001 location. So this is a 4001 location. So that's why this return address, it will be stored in the SBR. What is SBR? SBR is a subroutine. SBR is a subroutine. Because after executing all the statements in the subroutine, it has to come back to the next instruction of the main program. So what is the next address of the main program? That is nothing but 4001. That is equal to CAR plus 1. Okay. So CAR plus 1. Okay. So that is 1. Next, if the condition is fails, then CAR plus 1 will be loaded into the CAR. Next, return. So in order to return back to the main program, the subroutine address, so this subroutine address 4001 will be loaded into the CAR. And last one is a 11. So 11, it represents the mapping process. Okay, so mapping process here. So 0 we are loading into the CAR of 0 bit, 1 bit, 6 bit. Next, DR of 11, 12, 13, 14 bits will be loaded into the CAR 2 to 5 bits. So here we can see. So these are the bits. This is CAR. Okay. So 0 we are loading to CAR of. So we have a data register. Okay. So this is a data register. Okay. So in the data register we have 0 to 11, 0 to 10, 11, 12, 13, 14, this is 15. So these 11, 12, these are the opcode fields. 11, 12, 13, 14. Next, this is CAR. Okay. Okay. So 0 will be loaded to the CAR of 016. 016. Okay. So the CAR size is it is a 7-bit register. 7 bits. So if you represent bits D0, D1, D2, D3, D4, D5, D6. D6. Okay. So 0 we are loading into 016. 016. Okay. Next, DR of 11 to 14 we are copying to 2 to 5. DR of 11, 12, 13, 14 we are copying to D2, 3, 4, 5. So suppose if the bits, if the DR register 11, 12, 13, 14 bits, it is having 1011. So then 1011. So this process is called mapping process. Okay. And symbolic micro instructions. Symbolic. Okay. So in the micro instruction we are using some fields. Okay. So we are using 5 fields. that are label, micro operations, CD, BR, AD. So these are the symbolic micro instructions. Okay. Label. So what is label? Label may be empty or may specify a symbolic address terminated with a colon. Micro operation. So it consists of one, two, or more, one, two, or three symbols separated by commas and condition field. So one of the condition. So already we have seen the conditional field. So that are unconditional, indirect bit, sign of a register, zero value in accumulator. So that are represented with U, I, S, Z. And BR, branching. So already we have seen branching, call, return, and mapping process. So the branch field should be one of the four. And address. So address, it may be a symbolic address, or it may be a name of the address, like next empty, or sometimes it may be empty also. So these are the fields. Okay. So here consider a fetch routine. So read instruction from the memory. So fetch routine. Okay. So basically we are storing a program in the memory, and from the memory the instructions will be fetched. Okay. So first we will read the instruction from the memory, then we have to decode the instruction and update the program counter. So micro instructions for fetch routine. So consider a small fetch routine program. So that is so when the instruction is fetched, some sequence of micro operations will be takes place. So that our program counter address will be the program counter address will be loaded into the address register. Next M of AR, okay, will be loaded into the DR. Next it will increment the program counter address. Next there is a mapping process. So already just before we have seen mapping. So DR of 0 to 10 will be loaded into address register, and DR of 11 to 14 loaded into CAR of 2 to 5, and 0 will be loaded into the CAR of 0, 1 and 6. Okay. So symbolic microprogram for fetch routine. Symbolic microprogram. So how we can represent the symbolic form? So here, what is a field? What is the name of this microprogram? We are representing a fetch. Fetch is the name. Microprogram name fetch. Next, ORG 64. What is ORG 64? ORG origin. That means this fetch routine program, it is located at the memory location 64 in the memory. So that is the meaning of the ORG 64. Next, so what is the operation we are doing here? PC to AR. So PC to AR. What is the condition type? Unconditional. What is the branching type? Jump. What is the address of the address? Next one, M of AR to DR. That means that is a read operation. Next, incrementing PC. So this is equal to increment PC. So increment PC. What is the condition type? Unconditional. Branch type? Jump. Address type? Next. Okay. That means after executing this current instruction, it will go to the next address. This one. What is the operation we are doing here? DR to AR. DR to AR. And next U. What is the condition type? Unconditional. What is the branch type here? Mapping. Because here we are doing a mapping here. So that's why mapping. And the next address of the next instruction will be empty. Here empty. Already we have seen. The address will be a symbolic representation, symbolic number, or it may be a name of the address, or sometimes it may be empty also. Okay. So binary representation. So binary representation of the microprogram for the fetch routine program. So ORG64. ORG64. That means where this microprogram is located in the memory at the 64 memory location. So 64 in binary, we can represent this one, 64. Next, what is the micro operation? PC to AR. PC to AR. So PC to AR, it is in which field? So total we have three fields: F1, F2, F3. So total. So every micro instruction, it is having this seven total. It is having 7 fields. So one is the name of the field, label, name or label, F1 field, F2 field, F3 field, condition field, branch field, address field. So total it is having 7 fields every micro instruction. So this is a address 1, 2, 3, 4, 5, 6, 7. Okay. So here, what is the first micro operation? PC to AR. So where is PC to AR? So PC to AR. So it is at the first field. So this PC to AR, it is not available in the this F2 field and F3 field. So that's why F2 field zeros, F3 field also 0, and F1 field will be 1, 1, 0. So these are the bits representation. So that's why 1, 1, 0 is this one, zeros, zeros. What is the condition type? U. So condition U, unconditional. For unconditional, bit sequences will be 0, 0, unconditional. So for unconditional, the sequence is 0, 0. So that's why 0. Next, branch. What is branch type? Jump. For jump, the bit sequence will be 0, 0. Okay. So after executing that current micro operation, then after executing that current micro instruction, next it will go to the next micro instruction. So where is the next micro instruction? It will be in the 65 memory location. So this is the next address of the next micro instruction. So that is equal to 65 in decimal. Okay. So it will comes here. Next, so read operation. Read. Okay. So read. So where is read here? The read. So read is at, see, in the first field not there. Okay. See here. So read. So here. So corresponding bits in F2 field 1, 0, 0. So the read, it is not available in the F1 field and F3 field. So that's why the F1 field should be 000, F3 field also 000. So that's why, see, 0, 0, 0, 1, 0, F3, 1, 0, 1, F3, F3. Okay, okay. See here. See. So read is completed. Read is 0, 0. In the first field, that operation is not there. And in the second field, read is there, 1, 0, 0. And next, increment PC. So where is increment PC? This one. Increment PC. So corresponding sequence is 1, 0, 1. So that's why we have represented 1, 0, 1. Next, unconditional 0, 0. Jump 0, 0. Next address after 65, that means 66. Next micro instruction address is 66. Then it will comes to 66 location. Again, in this, what is there? DR to AR. DR to AR. Where is DR to AR? DR to AR. So this one. So is that DR to AR is available in the field 2? No. In field 3? No. So what are the corresponding bits in F1 field? 1, 0, 1. So the F2 field zeros, F3 field also zeros. So 101, 000, 000, condition type U, unconditional 00, mapping. So for mapping, what is the bit sequence? 1 1. So this is a mapping. So the bit sequence is 1 1. So that's why 1 1. Next. So here we are doing some mapping process. So that's why the address of the next instruction will be all zeros. Okay. So this is our presentation of the binary micro operation for fetch routine. So symbolic micro program. Symbolic. So see here. So already we know the control memory is having 128 words and each word size is a 20 bit. So in that 128 words, the first 64 it can be used to store the fetch routines or it can be used to store some routines, micro routines for 16 micro operations and the remaining 64 words can be useful to store the fetch routines, fetch or indirect routines. Okay. So first 64 words. So every operation, every micro operation, it takes 4 memory words, 4 memory words. So that means if you divide 64 by 4, then you will get 16. You will get 16. So that means we can store 16 micro routines. We can store 16 micro routines for the first 64 words. Okay. So how many micro operations we have? We have total 16 micro operations because in the instruction format the opcode bits are 4 bits. So that means 2 power 4, 16 operations we can perform. 16 operations. So for every operation, one micro routine is required. Okay. So this is for add, branch, store, exchange. Okay. So this is one. So first one is a add. So these are the 4 micro operations. So these are the 4 micro routines. Okay. Similarly, total we can write for 16. We can store 16 micro routines in the memory. Okay. So first one is a add. So add is one micro routine. So in order to store this micro routine, then it requires 4 memory locations. So that are 0 location, first location, second, third. So total 4 location. So the next micro routine it starts with 4. Next micro routine it starts with 8. So like that, all the 16 micro routines we can store in the first 64 micro memory words. Okay. So first one is add, and its its micro operation is a NOP, condition type I, indirect. Next call, address, indirect. So NOP. So its operation is a NOP. NOP. So what is the condition type I? If the micro operation is having indirect bit I, that means we need to go to the memory in order to calculate the effective address. Okay. So what is the branch type? Call. What is the address? Indirect. Indirect. So indirect. So that's why we need to go to the indirect routine. Okay. It will go to the indirect. Then read. Because we are performing a add operation. We are performing a add operation with the contents of accumulator and the memory. And the memory. Okay. So read. Read. Condition type U. Branch type jump. Address next. DR to AR. DR to AR. So data register. Because so First, we have a operand in the memory. We have a operand in the memory. Okay. So from the memory, that effective address, first we need to load into the data register. So M of effective address will be loaded into data register. So that is a okay. First, this is a read operation. After reading, this DR data will be loaded into the AR. Okay. After that, condition is U type and return. So it is a subroutine. Indirect is a subroutine. After executing, it will return back to the here. So next one, read operation. After reading the value, we need to perform the addition. So condition type U, branch jump, and it will go to the fetching. So once this addition is completed, the next micro instruction will be fetched from the memory. So that's why it will be fetched. So it will coming back to the fetch, and the next instruction will be fetching. So like that, all these micro operations all that micro instruction will be executed. And this is a binary micro program. Okay. So before writing micro program, first we need to write a symbolic micro program. If you write a symbolic micro program, then it is very easy to represent in the binary. Okay. So first micro routine is a add. So every micro routine, it takes 4 memory locations. So 0 memory location, 1 memory location, 2 memory location, 3 memory location. So 0, first memory location is 0. So in binary, it will be represented with all zeros. 1, 2, 3. So these are the binary representations. So first one, add. So here, see here, add. What is this operation, micro operation? NOP. NOP means 0, 0, 0, all zeros. So that's why F1 field all zeros, F2 field all zeros, F3 field all zeros. What is the condition type? I, indirect. Indirect means 0, 1. 0, 1, condition type. Next, branch type. What is branch type? Call. For call, it is 0, 1. 0, 1. Okay. Next, after executing, what is the address? Indirect. Indirect. Where is indirect? Here, indirect. So after, so the program control will be transferred from here to here. Okay. So see here. What is indirect address? This is indirect. So this is 67. In binary, this one. So that's why this address is specified here. So that means whenever this first NOP is executed, then it will return coming back to the indirect routine. Then it will execute. Okay. After that, next read. What is the next one? Read. Okay. So corresponding micro operation field. So this is 000, 100, 00. Next, unconditional. Unconditional means 00. Jump 00. Next means next instruction address. What is the next instruction address? 2. So 00. This is 2. Next, it will comes to second memory location. So in this way, all the micro routines we can store in the control memory. So this is we have discussed about the micro program example. So till now we have seen the format for the instruction and micro instruction format, and how we are generating the micro program. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.